Hello, hello, hello. How you guys doing? TTV Kitsos, thanks for chatting. First time chatting. Hopefully it won't be your last. I'm not gonna buy viewers though. I think that just is doesn't work out in the long run, but thanks anyway. Okay. All right, let me just turn down the music real quick. Okay, all right. Boys, girls, anything in between? How you guys doing? You guys having a good Tuesday? It's almost Wednesday. Week's almost over. I hope you guys are having a good time, because we have a fun stream lined up. Man. You guys are new viewers if you don't know. Usually I do Celeste stuff. I will do Celeste stuff later on, but today is special. Today is Tuesday. Okay? STEM Tuesdays. No longer Tech Tuesdays. We rebranded. That's right. We rebranded. We did the market analysis. We needed to rebrand. So now we're doing STEM Tuesday. Okay. So before, usually I do a PowerPoint of current events and just like talk about that and do all this work and then like do like, well, I shouldn't make it seem like that. I did this I changed it up to get out of work. I kind of did, but I also wasn't feeling passionate about it anymore. So usually I just make a PowerPoint, do like the, talk about the current events, about the current tech stuff going on, talk about that, make it hopefully fun and engaging for you guys. But I want to take a break from that. You guys want to know why? It's because every week I was real sick and tired of just getting AI. Always stupid AI news, not even good AI news. Like when ChatGPT, we had so good. When ChatGPT came out, we had so good AI news every day with some update with ChatGPT. Remember the whole, they tried to get Sam Altman not to be CEO scandal. Oh my god, that was so good. But now it's just stupid. Now it's like, oh, AI is Nvidia is worth trillions of dollars because the people refuse to say that we're in a AI bubble, like we are in a .com bubble. It's just real stupid, guys. AI, you just choose you choose a noun and then just add AI to it. That really seems like how some of these businesses are happening. Restaurant for AI. It's just AI restaurant, AI cows. I don't know. It's just I'm really sick of it. So new direction. We'll still do STEM related stuff, but I think where my skills lie is explaining stuff. So I think what I'm gonna do is like try to usually have a topic in mind. I have videos I want to like react to. That's kind of what we're doing right now. In the future, I have some other ideas. Maybe we actually code some stuff up, build some stuff on stream, just do some tech STEM related thing on today. Don't want to be like boxed into only having to do like a history PowerPoint summary. I might do a history PowerPoint summary again, in the future for STEM Tuesdays, but I don't want to just really box it in, if you guys know what I'm saying. So yeah, I'm in a pretty good mood. The last video I posted on this channel, on my YouTube channel, was not a 10 out of 10. Which must sound weird if you're not a YouTuber, but they rank your videos from 1 to 10, so you want a 1, not a 10. My last video was 2, so I'm really happy. My first one, that's number 1, doesn't really count as number 1. So yeah, we got number 2. I'm really happy. Yeah. We're gonna do new stuff. We're gonna do new stuff this time, so I'm really excited about that. Yeah. You guys are like, why aren't you just getting right into the videos? Because I'm a streamer. Okay, I have to delay the content. Also, this is a good way to practice talking to the camera and getting used to being comfortable. I have to get my 10 minutes of yapping. I have to do the intro yap session. Then move on from there. Mm-mm-mm. Mm-mm-mm. Hmm. So, man, do I not really have that much to talk about after 3 weeks of not streaming? Have nothing to talk about, really, Aries. Really. Do I really want to? No, I don't want to talk about that. Some of that stuff's too personal. Yes. Um, yeah, guys. I don't know. Oh, you know what? Guys, this is foreshadowing for future streams. But I'm getting really into electrical engineering. Like, it's a problem. Okay. And when like, I'm not an electrical engineering major, but I'm really considering going back for like my master's for like computer engineering or electrical engineering. And like, I'm considering it more every day. I like really don't want to go back to school, guys. I'm like really considering it. And it's gonna laugh. The thing that got me into it, I think that really made me consider it, because one day I just got recommended a Redstone video, and I just keep getting recommended Redstone videos because I watched the whole video. I just was so interested in it, and now, guys, I've watched so hours of Redstone videos. It's getting a problem. We're gonna make a computer, and we're gonna remake Snake. We're gonna remake chess and Minecraft. And guys, this is becoming a problem. Okay. You know how I know this is a problem? I've never played Minecraft. That's why this is a fucking problem. I haven't played a single second of Minecraft. I've watched so many hours of Minecraft videos. This is a problem. This is a problem. So get ready for that in the future. Who knows? Might make a circuit live or something. I don't fucking know. I don't know how electrical engineering works. That's why I'm studying it. Yeah, it's getting to be a fucking problem. I want to build shit. Just I like making websites are cool, but like something physical, something that can like turn on and off. That just seems so fucking cool. And then you combine the two together. Oh my god, be actually goated with the sauce. All right, that's enough yapping. All right, so right guys, I know we got the fancy background, so you already know Tech Tuesday time. Tech Tuesday time. Mm. Boys, the plan is simple. How do you guys like my totally original intro? Mm. Boys. All right. The plan is simple. Actually, it's really simple. Okay. So today, I realized that there's a video online. Okay. I love two things. I really love two things. I really like math and nerdy and science, just any nerd shit. Okay. And I love animations. Okay, I'm not one of those. I'm not one of those liars too who like says they like animation, but they only like anime. Okay, because they're weeps. Okay, no, I like all forms of animation. Okay, so I like animation. I love math. I love these two things together so much. Okay, I've watched so probably thousands of hours of content in both these things easily thousands of hours of content. Okay, so want to get news? My recommended that there's this fucking guy named Alan Becker who makes stick figure animations. And he recently made one called Animation vs. Math, and another one called Animation vs. Geometry, and then a third one called Animation vs. Physics. I had to fucking watch it. I had to fucking watch it. I needed to watch it. I did watch it. I remember it being really cool. I don't remember much of it though. I remember it being cool. I remember the feeling I got. So, when I was thinking about that, I thought it'd be a really cool stream because I majored in comp sci math. That's right, two. Okay, comp sci and math. I think it'd be really cool if I rewatch these videos and try to explain some of the math concepts that are coming up. Totally original idea. No one else has done this before, I'm sure. First one right here to do this. So, I think it'd be a really fun idea to do that. I think I have a lot of insight that I can give other than just, oh, this looks really fucking cool. I watched it once as monkey brain, this looks really cool, like cool choreographed fight, and I'll also get it as the this the math references. So yeah, that's the plan. I think it'll be a really fun time. I think it's gonna be a really good video, and yeah, get ready, jump in. Let's just jump into it. All right, so I have the videos over here. Okay, so it's playing over there. I need to pull it up. Kowalski. Okay, so it's up. Now it's full screen. Okay, awesome, 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 awesome. You make this bigger. I like them big. I like them big. I like them. Okay, cool. All right, so this is animation versus math. So what I'm going to try to do is that whenever... Oh, wait, this is so... I didn't even... Oh my God. I didn't even plan this. Wait, but this is actually so goated if this works. Okay, you guys will see. Okay, so what I plan to do is that as I watch this, I'm going to be watching it, reacting to it, you know, pausing to give my insights every once in a while. If you don't like pausing, you want maybe one of those reactors, you just does that the whole stream and doesn't react. I'm not Jinxie. I'm sorry. I'm actually going to talk about my thoughts. Yeah. So what I think I'm going to do is if I have some insight or some like math thing, like I want to write down or explain, then, oh, you can see me. Wait. Then, yes. Wait. Yes, it's normal. Yes, I'll write it down and you'll see it in my terrible handwriting. Yes. Don't worry about shapes. Don't worry about that. Forget about that. No. Don't worry that says shapes. Actually, just don't worry about it. Actually, don't worry. Okay, cool. Don't worry about the shapes gray stuff. Okay. So that's like my drawing notepad that I want to draw. But today we're not going to draw on it. We're just gonna do math stuff in it. Math pad. Okay. All right. So without further ado, we're gonna watch this video. Yeah, and just talk about my thoughts. One. Of course, the first natural number. Natural numbers, of course, mean the counting numbers 1, 2, 3, 4, 5, 6, etc. 1, you know, it's 1. What else is like, that is true, but maybe this is not true, because if you guys watched my latest one of my latest STEM Tuesday videos, you will know that this is actually controversial now. This video is actually a little outdated, because if you guys watch the most recent one, you should know that 1 actually equals 2 sometimes. We go by Terrence Howard. Now, I'm not, you know, as smart as Terrence Howard, so I can't exactly explain how 1 equals 2, but if you want to know more about that, you can watch my other video talking about that and going to the proof. So a little outdated. One plus 1 equals 2. Yep. Actually, you guys are gonna hate me. I'm pausing 4 times. It's not even 30 seconds in. You guys hate me. So one thing that just came to my mind though is that so 1 plus 1 equals 2. You may think that this is like obvious, and like of course one thing plus another thing equals 2 of that thing. Of course, like you've been using math so long, of course it makes sense to us. But have you ever thought, like, how do you even prove 1 plus 1 equals 2? And the proof to prove 1 plus 1 equals 2, I'm pretty sure. I'm pretty sure it's like hundreds of pages long just to prove 1 plus 1 equals 2, which is kind of crazy to think about. But then I thought about it a little more. I guess it makes a little bit more sense. You have to define what 1 is. You have to define what like adding is. What does equality even mean? And then you have to use like set theory to like basically say, well, 1 is actually a set. What is a set? A set is just a group of things. So 1 is just a set, a group of things that have only a singular element in it. And it's like, oh man, it just gets really just to prove 1 plus 1 equals 2. So yeah, there's a lot of stuff in math that we kind of take for granted, but it's actually, you know, we only got here by living off the successes, off the bridges of our ancestors. So, all right. So anyway, 1 plus 1 equals 2. True. Also, I haven't said it yet, but I like this like music. I like what's going on with the music here. Really cool. I like the vibe. True. 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 Okay, so right there, that's an example of a. Oh, actually, I don't need to say what that example is. It's just 2 equals 1 plus 1. We already know this. We already saw that 1 plus 1 equals 2. So, of course, you could break 2 down into 1 plus 1. Just like you can break down any number into just addition of other numbers. Or, I don't know if it talks about it. Or you can break it down any numbers to a bunch of multiplication of some prime numbers. So, yep. Yep. Oh, but we can go a little faster than that. We got our 20. True. We did it. True. Subtraction, obviously the opposite of addition. I don't need to say much. Yes. 0, very good number. 0, one of the most important numbers, up there with 1. I think I read somewhere that like some societies, look, there's this podcast about like there's a linguist, and like what he was talking about is that he was trying to learn languages from like other cultures or whatever, from like undiscovered languages from cultures. What he realized is that the way some people think about numbers is so different from us. For example, like the culture he was describing, they didn't have a concept of 1, 2, 3, 4, 5. They didn't even have a concept of 0. They had a concept of little, a little, medium, and a lot. That was the only numbers he had, which I guess makes sense. And they, like, given their culture, you just live in like hunter-gatherer society. Do you really need to understand the concept that there are 2 of a thing versus 3 of a thing, or do you only need to know the concept that there's a lot of it? So I thought that was a really cool thing. The idea that some cultures, like for a long time, the idea of 0 or even negative numbers, I'm assuming they're gonna get to negative numbers next, wasn't even like a concept. The idea that negative numbers really only showed up where when we got to debt and money. So it always goes back to money. Yeah, exactly. Yeah, negative numbers, just like I said. Yeah, we didn't have the idea of negative numbers for a long time. It makes sense to a lot of people, but like, what is a negative number? Oh, okay. All right. So if you don't understand that, like, this probably looks crazy because we went from -1 to e to the pi I. E and pi are both irrational, meaning you can't express them as a fraction. So there's decimals that go on forever and ever and ever. And I isn't even a real number. It's an imaginary number. So how is it when you put them all together, you get -1? How is this possible? Luckily, I think I could actually explain how it works on here. 2 e. Oh man. Okay. Actually, okay. Maybe not. I need to. Ooh, I'm at Conundrum Boys. I can. Ooh. Okay, I can use Canvas. I can use the Paint. Ooh, I can use MS Paint, but I don't have like a stylus or something. I would have to use my mouse, and this is better. Okay. If this doesn't look good, we can just in post. We'll just make it look better on the screen. So anyway, so e to the pi I somehow equals -1. How the fuck does this happen? You may also see this equation written as the following, as e to the I pi plus 1 equals 0. So this equation right here is known as one of the most beautiful equations in math. Reason why it has 5 of the most important, famous numbers in all of math, as e, as I, as pi, as 1, and as 0. And it looks very simple. So all those things together make it like a very elegant, very pretty to look at equation, in my opinion, and a lot of other mathematicians' equations. The real question is, how the heck does this work? How do you get from do you even get this? So to do this, we're gonna have to use some fancy calculus math. I swear, just stay with me. It's not gonna be as bad as you think it is. You're just gonna stay with me, okay? So we're gonna start with e to the x. Okay. Actually, wait, I forgot. I didn't even explain what e, I, and pi were. Let's go back. Let's roll back the tape. Okay, before we go to this equation, let's explain what these things are. I is an imaginary number. It is the square root of -1. Okay, it's the square root of -1. Imaginary number is probably a bad term for it because it implies it doesn't exist, I guess. It definitely exists. It's kind of, I think complex number is a better way to describe it. Complex, so I is a complex number, and I equals square root of -1. You cannot square root a negative number, therefore, you know, imaginary is not a real number. You cannot square root an imaginary. You cannot square root a negative number. Because the square root is something where you can multiply two things together to get that number on the bottom. So for example, the square root of 4 equals 2 because 2 times 2 equals 4. There are not two of the same number that can get you -1 because if you multiply two positive numbers together, you get a positive number. If you multiply two negative numbers together, you also get a positive number. So if you have a negative number underneath square root, then this does not make any sense. So that's how we have I here. That's how we have I here. Square root of -1. Yeah, so that's what I is. Pi, of course, equals something like 3.1415926, blah, 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 blah. But what exactly is pi? Pi is just, let's say you have a circle, any circle at all, actually, any circle you could possibly think of. There's a thing called the diameter. The diameter is just like the width of the circle, okay? This is the diameter, it's just the width of the circle. It's the line that goes from one point of the circle to the other side of the circle and also goes through the center of the circle. That's what a diameter is, okay? The circumference of a circle is just like the perimeter of the circle. It's just the whole length of the circle wrapped around. So that's what circumference is. So this is circumference. Down here, this is diameter. So pi is just the ratio between the circumference or diameter. So the idea is no matter what size circle you get, the ratio between the circumference and the diameter of any circle you could possibly get of, it's always pi. That's what pi is. That's how pi was discovered. It's no matter what circle you make it, you always get the same ratio. That's what pi is. So I described I described pi, but E. I think E gets a little bit more complicated. I'll do my best to try to explain this. Okay. So E, how do I describe E? Oh, I can describe E with money. Okay. So you guys have money, right? Okay, well, maybe you guys don't because everyone's struggling right now. But imagine you had money, okay? When you have money, you put it into a bank or a savings account, for example. And the bank account has interest. Basically means that the longer you put the money in, the more appreciative that the bank is. And they'll give you some money for just keeping the money in the bank. That's essentially what interest is, okay? So let's say, for example, that you have $1 in the bank. You start with $1, okay? And let's say this bank is really generous. It has 100% interest, okay? 100% interest for the savings account. I know, really good account. The catch is it only compounds once per year, okay? It only applies to interest once per year. So usually, I'll just say this, if you never had a savings account before, 100% is a ludicrous interest amount. You'll never get that much. You'll be so happy if you get that much. You'll never see that ever, okay? And also the idea of compounding once a year is also kind of great. Usually it compounds like maybe like once per month or just like or monthly or maybe like bi-weekly or just it doesn't apply once a year usually. So let's see this. So let's say we have this hypothetical bank and the bank compounds 100% once per year. We start with $1, okay? Now we're going to add the interest. The interest is going to be 100% of what's in the bank. Okay, we have $1. 100% of $1 is 1. So that means after the end of the year, we'd have $2. Pretty good. Okay, let's see if we can change things up a little bit. Let's say instead the bank offers you 50% interest, but they apply it 2 times per year. 50% interest, but they apply it 2 times per year. Just intuition. Do you think this is going to be worse than what you had before or better than what you had before? Just think about that real quick. Let's find out. So we have $1 in the bank. Now we're going to add 50% interest. 50% interest of 1 is 50 cents. Now we're going to add 50% interest again, but we're going to do everything in the bank, not just the original one. We constantly compound based off what's currently in the bank. So now we're going to do 50% interest on $1.50. And that is 75 cents. So now we're also going to add 75 cents. And look at that. Now by the end of the year, we're going to have $2.25. Wait a minute. We had a smaller interest amount. But we compounded more frequently, and we ended up with more money. That's pretty good. You may wonder, wait, does this mean if I just keep this pattern going, I might get more and more and more money? And you might be asking too, how does this relate to E? I will get to that. I promise. So yeah, and your intuitions are right. Maybe we do 33% interest. We do 3 per year. We'll get more money. And we do 25% interest and 4 per year. We'll get even more money. And you may be saying, how am I getting 150, 33, 20? Where am I getting these percentages from? So the way I'm getting these percentages is like this. I have 100. I have 100%, or 100 over 1, compounded once per year. Then I have 100 over 2%, compounded twice a year. I have 100 over 3%, compounded 3 times a year. 100 over 4%, 4 times a year. And that's how I'm getting the percents, okay? So the idea is you keep doing this, okay, you'll get more and more money. But the amount you get each time is going to be a little smaller. So it's going to be a little smaller each time. So if I just do the math real quick, I don't have my calculator. Oh my God, I don't have my calculator. Okay. So I'm just going to do the math real quick just for $3. And I think in the edit, I'm going to show like what it is over the rest of them. But if we do it for $3, we get, let's see. 1, 2. Let us see what we get. There we go. If we do it for $3, we actually get $2.37. So we're still moving up, but did you notice something? From here to here, we jumped up 25 cents, but from here to here, we jumped up only 12 cents. So we're still increasing, but we're slowing down how much we're increasing over time. So that implies to me that we're converging. We're getting closer and closer and closer to a value, okay? That's the idea. We're getting closer and closer to a value. And that's exactly what E is. The idea is if you had this over and over again. So you can imagine if you theoretically had like an infinite amount of percents per year you're compounding it, and you had like a super small amount of compound of this percentage. The idea is that this tends to infinity as this gets bigger and bigger and bigger and bigger, and you compound more and more and more and more frequently. The idea is that you will eventually approach E. And that's what E is. And written in other terms, the limit as n approaches infinity of 1 plus 1 over n to n. This here looks complicated, but this is just the math we're doing to get the final answer for the bank problem. The limit as n approaches infinity of 1 plus 1 over n. 1 over n represents the 100% or the 50%. N represents how many times you're compounding the interest. The idea is when you limit as n approaches infinity, so as n keeps getting bigger and bigger and bigger, this is E, which equals about 2.71 something. So yeah, now you know something. That is E. That's how E was discovered. It was with math. Yeah, of course. It was with money and banking. That's what E is. That's how you get E. I know my chicken scratch looks really bad, so hopefully in the edit this will look a lot better. On the YouTube video, this will look a lot better. But yeah, That's what E is. It's just a compounding interest thing. That is what E is. So, going back to this, we know what E is, we know what I is, and we know what pi is. So let's go back to E to the I pi equals -1. All right, so how are we going to figure this out? How do we get we did all that just to show this. How do we get to all of this? Okay, so here's how we do it. So first you need to have this thing called E to the x. Okay, and what I'm about to say, okay, you just gotta take my word for it. I'm not gonna prove it. I've already taken enough time away from the video. I'm not gonna show you. Just have to go with me. So E to x equals 1. Wait. I want to make sure I'm not messing this up. Oh, there we go. Okay, so E to the x equals 1 plus x squared over 2 pi plus x cubed. I mean, did I say 2 pi? I'm getting fucking sleepy. No. Okay, let me say it again. E to x equals 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, etc., etc. So if you want to find e to the power of x, you plug in whatever x is, you put it into this infinite summation, and that's what e to x is. All right, so that's the first thing. Second thing, you just gotta take my word for it. I'm not gonna show it, I'm not gonna prove it, that's just fact, okay? So now, e to the ix, okay? Another thing, actually, yeah, another thing you gotta know is what cosine x equals to. Cosine x. Not gonna go over what cosine is, so you just gotta know what cosine x is. Infinite series. All right, here we go. So cosine x, infinite series. So cosine x goes back to SOHCAHTOA, goes back to triangles, etc., whatever. But we want to rewrite this as an infinite series. This is equal to 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, etc. So like alternate signs, but it's only the even ones. Sine x, if we're writing as an infinite series, sine x as an infinite series equals x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, etc. So again, it's also alternating, but this time it's only with the odd numbers. So that's really cool. And this is going to be really helpful to figuring out how we prove this crazy equation right here. So we just figured out the infinite series for e to the x. So now let's say with x, we replace x with I to the x. So wherever we see an x, we're going to replace it with I to the x. We're going to rewrite this whole series again. So this is going to be 1 plus I to the x plus I to the x squared over 2 factorial plus I to the x cubed over 3 factorial plus I to the x to the 4th over 4 factorial, etc. So now we gotta go back to what I is. I equals the square root of -1. So that means I squared equals -1. That means I cubed equals -I. And that means I to the 4th equals 1. And then I to the 5th equals I, and then it just keeps repeating in that pattern over and over again. So that's good to know, because now we can simplify this equation up here equal to 1 plus I to the x plus, we know what I squared is, that's -1. So it's actually going to be a minus x squared over 2 factorial. I cubed, now it's going to be minus I to the x cubed over 3 factorial plus I to the 4th, that's going to be 1, x to the 4th over 4 factorial, and it's going to repeat that. So let's try to get the ones with I on one side and everything else on the other side. We can rewrite this as 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial on one side plus I on the outside, x minus x cubed over 3 factorial plus dot dot dot. All we did, we just simplified it, okay? We took all the ones that don't have an I on this side, and then over here we have took out the I and just have everything else on the inside. So now should be an aha moment, or you might not have the aha moment, but this is where I had the aha moment where you realize this right here, 1 minus x squared over 2 plus, that's cosine, and this x minus x cubed, that's sine. So we can rewrite e to the ix to equal cosine x plus I sine x. So this alone already looks pretty cool to me, but then we're at our very last step. All we gotta do is replace x with pi, e to the I pi, and then we replace cosine pi plus I sine pi. Cosine pi equals -1, sine pi equals 0, so this gets canceled out, and we're left with e to the I pi equals -1. My opinion, one of the most beautiful equations. Really, really cool. Really, I know that was a lot of math. I know I yapped a lot, and we kind of lost the plot and kind of forgot what we were going back. But I think that's a really cool explanation on how this works. What E is, what everything. We guys learned something. I think this is really cool. So that's how this guy turned -1. Going back to the video, this is how he turned -1 into e to the pi, e to the I pi. I think that's really fascinating. So going back to the video. I think what they did there is it kind of implied that like I is on the complex number field. It's not a real number, it's complex. So it's kind of like going, it's like it has its own plane. It's an imaginary plane. It's like not real numbers. It goes to its weird state. And you say like, but it was e to the pi I pi. How is that not? Remember, e to the I pi is -1. That's a real number. So the moment I put an extra pi in front of it, it entered like the imaginary number realm. So I think that's a cool way to do that. True. True. A negative times a negative equals positive. Yep. True. Multiplication is really just glorified addition. Pretty much everything, addition, subtraction, multiplication, division, it's all addition in a way you can think about it. You can think about subtraction as just adding negative numbers. You can think of it multiplication as just glorified addition, and then division is just glorified subtraction, which if you already says that subtraction is glorified addition, you know, just adding negative numbers. And you can think of it as all addition. But yeah, of course, yeah, that's what multiplication is. It's just doing more addition. Yep, and you can represent the same number in multiple different ways. Division is same as subtraction, yep. Which I think hopefully intuitively thinking of division as subtracting actually helped me a lot understand why dividing by 0 kind of breaks things a lot. Because if you think of dividing, it's just you just keep subtracting. So like 6 divided by 2, you can think of that as just subtracting 2 until you get 0. And you do that 3 times. So that's why 6 divided by 2 equals 3. But let's say you want to do 6 divided by 0, okay? So if division is glorified subtraction, you're going to keep subtracting 0 until you get to 0, but you're never going to get 0. So that's why divided by 0 is cursed a little bit. That made more sense to me why, you know, dividing by 0, you get really funky. You can't do it. Exactly, yeah. That's why dividing by 0 is so cursed. Yep. Yep, of course. You represent. Yep, and exponents are just, again, glorified, you know. I should stop saying glorified. Glorified check? Whenever I say glorified. Yeah, but exponents, of course, they're just, you just multiply 6 squared. That just represents 6 times 6. Of course, 6 cubed would be 6 times 6 times 6. Yep. Remember, it's called squared, you know, because you think of it like you add up all that, you can think of it as a square. And when it's cubed, you can think of it as a cube of additions, you know, so that's a nice touch. So they added there. Squares, yep, cubed is a cube. Therefore, if you get to the 4th dimensional stuff and you're like, I don't know. Negative exponents completely fine. It's just 1 divided by the whatever it is. So, or to negative second, it's just 1 over 16, etc., etc. Yeah. Exponent should never be able to give you 0 unless the base number itself is 0. Remember that. Anything to power 0 is 1. If it has a positive of exponent, it shouldn't be 0 unless the base is 0. If it has a negative exponent, it shouldn't be 0 in the first place. Square root 2, another famous irrational number. Yeah, probably up there, another famous irrational number. We've known about this number for a long time. The way we actually found this number is with right triangles. So you could think of this like we have a right triangle right here. Idea is, if I know these two don't look the same, but imagine these two sides were both 1. Then we can go back to our man Pythagoras, you know, and hopefully you guys remember this. A squared plus b squared equals c squared. To figure out what this is, a and b are these two sides, so we have 1 squared plus 1 squared, so that equals 2. So 2 equals c squared. We solve by taking the square root on both sides, and we get c equals square root of 2. This right here is the square root of 2. So even the Greeks back then were able to get the square root of 2 consistently by doing that right triangle method. Yeah, it's also irrational. Rational numbers mean that if you divide them, you cannot express them as a fraction no matter what. It's an infinitesimal, so yeah. Oh, yep, there we go. You can just add them up. Yep. Yeah, I is really weird. Oh, there it is. Because I times I was that -1, and then times I again. There we go. Because we know e to the I pi equals -1. So we get this, then we add an I on the end, and that's how we get that. See, my explanation before wasn't for nothing. Otherwise, you'd be so confused. I love how it runs. Oh, that's a nice touch. Okay, so it went back, it tried to go in the complex number field because it tried to go in a complex number field because it spawned an I from it, because again, if it has I to the e to the I pi, that equals just negative I. So you can go to the complex field, but then you're going to multiply. He threw an I at him, multiplying another I to him. And by multiplying another I to him, this whole thing turned into positive 1. Yes, turned into positive 1. Making him go back into the real number. So, oh yeah, that's a nice touch. That's why he's so confused. He's like, what? Oh, that was, oh, see? It's right there, cosine pi, I to the sine pi. There we go. We figured out how we got that equation before. Right here. There we go. Makes sense. Did you just throw a negative at him? And like reverse. That's nice. Hey, it's a nice touch. What? I pi minus pi. What is that? I pi minus pi? What's that equal? Wait. E to the I pi minus pi. That's the same as e to the I pi divided by e to the pi. Yes. That's the same as -1 over e to the pi. I don't think that's a... Wait, is that like a simple number? Wait. I feel like I'm kind of dumb. Wait. 1 divided by... No, you don't get a simple number. Okay. Maybe I'm doing my math wrong for this. That was really cool. Don't know how he did it. I'm kind of confused how he did that one. I'm multiplying the speed. That's really nice. Negative turns around. True. Are they gonna cancel each other out? Oh no, they're just gonna... That's fun. Oh, they do cancel each other out. Wait. Is that why they're... Oh, wait. They are canceling each other out. That's why they... Whenever they... one of them's a +1 and another one's -1. That's why whenever they get 0. That makes a lot of sense. Oh, that's a nice touch. That's cool. E to the I pi over 4. Oh, I see. Oh, okay. Now I feel kind of dumb. Okay, I see. So you can actually turn... So e to the I pi, or e to the ix, you can rewrite that as with sine and cosine. And with sine and cosine graphs, you can... those are all curve-based. Oh, I see. I think I see what it's doing. Those are all curves. So I think it's somehow... So I think... Actually, wait a minute. Let me just real quick. Wait. E root y. Oh, that makes a lot of sense. That makes a lot more sense. Oh, okay. I see it. Okay, I think I understand. So the idea here is that e to the I pi over 4, you can put this into the cosine plus I sine x function. And when you do that, you'll get a complex number. You'll get a real part that doesn't contain I, and you'll get an imaginary part or a complex part that contains the I in it. And when you do that, you can actually graph it on the real complex plane. And when you do that, I think this is what you get. That's how you get the curves. Which, if I understand that correctly, that's really fucking cool. I think that's really fucking cool. Oh, and that's probably why. Oh, and I'm sure if he plugged that in, that's how he got. Oh, okay. That's how he got the full arc. Okay, that makes sense. I think. Yeah, I also like this music. Oh, true! Did he figure it out? Use the curve. They figured it out. True. Yep. Oh, it got to... Yes, the complex... This is how you graph complex numbers. You have a real axis, and then you have a complex axis. The real axis only has real numbers, and the complex has I. Yes, exactly. Okay. Yes. Okay. I'm not crazy. So you graph it just like X and Y, but, instead of, yeah. But the horizontal line would be where you plot your real number, and then your y, your vertical axis be where you plot your imaginary number. Okay, yes, I'm not crazy. I remember my math. Oh, true. That is length 1. Oh, true. Gonna make it bigger. Yep. Circle. Yep. If you change theta, it's gonna change the angle. Yep. There you go. Theta, of course, a famous way we express angles. We use to express angles. Theta over r. Yes, there we go. We have cosine and sine. To the, oh yeah, and then we're gonna get the cosine graph. We hit them together. We get them both at the same time. Just real quick, do you think Alan Becker also on the side just knows a lot of math? I hope so. I don't want to feel that inadequate. I hope he's just a good animator. He just has a math friend. Because otherwise, oh my god. There we go. Wait, what? Oh, there we go. So this is just the definition of E. So E, so before I said that E was just the infinite sum of just like 1 plus x squared over 2 factorial, and this is just the formalized way to just write out that summation. But instead of x, it just replace x with I pi, and that's it's just E. This is just E. This is just E to the I pi. So that's another fun way to express it. What is it shooting out? Oh, is it shooting out terms? Oh, there it is. Yeah. 0, yeah, 2. Oh yeah, it's shooting out all the terms in the, yeah. Oh, that's, yeah. Okay, yeah, that's cool. So 9, 10, 11, yep. Oh, he got him. He got him. Oh, he went the other side. He reversed it because he put himself with a negative. Ooh, oh. True. Oh, I see. So, oh no. I see. So, oh no. So these are just other ways to also write cosine and I to sine x, and it's just from there. As you can see, e to the I pi is within these definitions. So that means you can get like an infinite like thing going on and on and on. Yep. Tangent. Just cosine over. Wait. What do you? Sine over cosine is just tangent. Yeah. Wait, what is tangent pi? Or he just didn't even do tangent pi. He just did. You got a function. The function, you put in something, you get out something. That's what functions are. Yeah, so many. Alright, change the angle. Is it gonna stop though? Oh no. Oh no. Oh no. Is it gonna stop at pi? Do I understand that correctly? Oh. Oh, he made infinity. It wasn't 8, it was infinity. What was that? Oh wait, every time he shoots it, it like adds another dimension space. So first it was just like 1D, then 2D, then 3D. Now it's 4D. Yeah, that was cool. Oh no! Oh no! They're forming the Megazord. Oh no! Oh no! He got. Oh no! He wanted that, and that looks like an integral. Do we have an integral? Integrals used. Integrals are used in calculus a lot to find the area under the curve. 0 to infinity. Oh my god. Oh, I'm pretty sure I can't do the math right now. I'm pretty sure on the right it's just an integral. So it's like if you solve this integral, you get this. That's what I'm assuming. Assuming? I'm not doing that off the top of my head. Why does it sound like it? Oh, he's back in the circle. What you gonna do, Orange Man? True. Cool. You can just spawn more of himself. Oh no. Oh. Oh no, he's done. Can I just talk about, like, other than mashup, this fight's like really good. Like it just goes back and forth a lot. I've never been bored watching this. This is like a 14-minute video. Alan Becker is great. I'm gonna watch more of his shit. Oh man, you got so many different ways to get pi in there. I mean, not pi, to get E from there. I saw a log in there. I see a bunch of factorials, a bunch of summations. Oh man. Oh no. Oh no. He's already dead. Oh no. Oh no. Oh, he's getting the F out of here. Oh, he's getting him. He's getting him. Oh, dude, he's in the imaginary verse, the complex verse. Oh, yeah. You see all the other imaginary numbers cracking through. All the crazy numbers. Yep, and we're real again. really understand what they're saying, even if they're not saying it. There's no dialogue in this. It's so crazy. Alright, he's gonna get them out of here. True? Oh, he's not going. True? Okay, we got another way to write E. Oh, I think I've seen that. Oh, yes, I think I've seen it. Wait, isn't that the way to... I think that's the formal way. Oh, God. I'm pretty sure this is the formal way, the formal function to express factorials, but for any number, I'm pretty sure that's what the function is. Pretty sure? Could be wrong. I'm pretty sure that's how it is. You can express factorials even for fractions and negative numbers. Oh man. You got him. Of course, all the special math symbols come out to see him out. And alpha null that represents all the natural numbers. The set of all natural numbers, so of course, is huge. Like, great video. Can you also say I love the music to this video? I didn't even. Oh man, there's so much stuff. I love this whole video. I love it a lot. Man, I might play the. I love that music so much. I need to steal that in other videos. Yeah, I hope you guys learned something. Yeah, like just the fight itself was really good, but even all the small references and like only like some nerdy guy like me would know this. I think that's really pretty cool. This is a really cool video. I kind of want to watch another one before I go. I don't want to go off that. I kind of want to watch the geometry one too. That plus end, of course. That was great. That was fantastic. I want to watch another one though. I will say I don't know as much about geometry as I do math, but it's a shorter video. I see this. I see this. I already know what that is. I have a feeling I know what that is. But why do I have a feeling? I'm pretty sure I remember watching this. I'm pretty sure. But let's check it out again. Okay, so yeah, let's check this out. Animation versus geometry. And guys in the chat, I have my question of the day. Algebra, geometry, calculus. Favorite math? Go. Tell me in the comments below and why it's obviously calculus. Calculus, best math, in my opinion. All right. I feel like I liked math, but I didn't start loving math until I saw calculus. Like I feel like I had a bunch of questions in my earlier math. I'm like, how do you possibly solve this? How do you possibly do this? And then calculus like answered a bunch of them. And then like I know like the day I learned about the revolving, you can make 3D objects because of calculus and figure out the exact dimensions, exact volume it would take up. I mean, I love this. I love this class. And then you find out the whole real world actually runs because of calculus equation. Oh my god. All right, what is this? Oh shit, that's a cool desk mat. I'm looking at my desk. I realize like I don't have a desk mat. I might buy one. I should. I might actually buy one of these. I like the red one. I really like, and this one's my least favorite. I like these three. Like this. But between these two, I don't know. I like them all for different reasons, but this one's my least favorite. I think they're all good. Well, shit. Well, it is what it is. Didn't this video come out like a year ago? What am I talking about? You have a circle, which makes sense to start a geometry video with. Oh, you got a line. You got a point. You got one to this one dimension, you know, because you have one line. That's it. Aren't you gonna come out? Man must be sick of just appearing in black voids. Okay. Yep. Okay, so we're gonna, yep. This is geometry, so the first thing you learn about are line segments. Lines first. Well, line segment, you have 2 points, you connect 2 points, you have a line segment. A line, I'm assuming they're gonna get to a line where a line is that one of the sides, at the very least, one or both the sides go on forever. Yeah. Yeah, so there's a line segment, you have 2 points, and you draw a line between two. As a point is how we connect it. So we have point A and point B. Those are points. So these are the basic concepts in geometry. That'll take a line because it will keep going on forever. You have C as the point, and then it just keeps going on forever. So that's a line. There you go. You intersect. Now you intersect two things together, and now you have angles. Because it's vertical angles. If you learn vertical angles, that means these two angles. You have two intersecting lines, and their two angles are vertical. That means these two should be the same, and that means these two should actually be the same. I'm pretty sure these two should be 132 because this line is just the segment is just horizontal. It's just 180 degrees. So these two should be the same, and these two should be the same. And he's just going to keep changing, but notice that when this one gets smaller, this one gets bigger, and this one also gets bigger, just so. Yep. Oh, we got our classic right angle. Very important angle. Yep. Up there it's 180. Yep. Notice the circle adds up to 360. That's a whole lot of stuff. Notice that these angles all add up to 360 because this is on a circle. Yep. Okay, this looks like ratios. Yes, I believe this is ratios. Okay, so basically it's saying that from A to here to B to here, these two are the same. These two are the same. It's saying if you go this distance divided by this distance, you get 1. That means these two are both the same, I think. Yes, okay. So now we're saying this side is shorter than this side because we take this to this and divide it by this to this, we get less than 1. Yeah, so this is just a ratio between how long A is and how long B is. And they represent the line segments. Oh, RGB. So that looks like you got close to the, it looked like it flashed gold for a second. So it looks like we're gonna get to the golden ratio. Let's see it again. I think golden ratio is like 1.6, I think. Yep. So what is the golden ratio? Basically the golden ratio is just I can describe it, I'll describe it in nature first and then mathematically. So in nature, in just paintings and just things that we all deem to be aesthetically pleasing, we notice that they tend to have like this thing called the golden ratio, or this perfect ratio between just their features that works. And if you guys notice this, you notice this in from things like the Mona Lisa, from real life flowers to even to Sonic the Hedgehog. These and you can wonder why are these so aesthetically pleasing. And it's usually because they have the golden ratio when in mind when drawing them, whether they know it or not. Yeah, so that's essentially what the golden ratio is. Of course, yeah, the golden ratio pretty much appears in like anything that's aesthetically pleasing. That's why, you know, I keep thinking, I think the most recent thing I remember, the golden ratio appearing actually in JoJo manga, JoJo Part 7. where there's a whole plot point about the golden ratio. In order to get his like his powers to get off, he has to understand the golden ratio. It's just, oh my god, I love part 7. I love part 7. Best fucking part. Best fucking part. How can you say it's not? It's dinosaurs fight the president, Jesus corpse. Oh my god, so good, so good. And they have the golden ratio as a actual in-universe mechanic for oh my god. Anyway, so that's what the golden ratio is. It makes things a lot very aesthetically pleasing. Appears a lot in nature. What exactly is the golden ratio? Is about 1.61 how exactly did they figure that out? I think one way to figure it out is actually with the Fibonacci numbers. So if you know the Fibonacci numbers, they're like 1, 1, 2, 3, 5. Basically, all you do to get the next number, you add the 2 previous numbers. So then we get 8, we get 13, and then we get 21, etc., etc. So these are the Fibonacci numbers. So the ratio. So one question somebody had is they wanted to figure out what the average ratio is between 2 numbers. They want to know the ratio between, like, let's say we had like, they want to know the ratio between xn and xn plus 1. xn representing a number and xn plus 1 representing the number after. And then with like some about math, a bunch of math, I'm trying to figure out I remember like a number file video about this, I think, that I think explains this better than I can. I'm trying to remember, to be honest. I'm pretty sure once you like solve this, you get the golden ratio, which I think is like 1 plus square root 5 over 2. I could be wrong. Let me look this up again. Golden ratio. Yeah, 1 plus square root 5 over 2. Okay. Yeah, but I can see the derivation. How exactly did they get the golden ratio? Wait, now I'm curious. Now I'm kind of confused how you get the golden ratio. Oh, I see. Okay. Okay, I understand. So basically, they want... I think I understand. So basically, they want to get the average. So let's say you have the Fibonacci numbers like this, okay? You want to get the average ratio, okay? So that's just the number before divided by you have the current number. No, you have the next number divided by the number previous. That's what this represents. You want this ratio, okay? And you're saying that this ratio. So let's like rewrite this as A and B, okay? A over B. So A represents like the next number, B represents a previous number. And you want this ratio to be the same for like every 2 sets of numbers, okay, in the Fibonacci sequence. So that would mean that this works for the next number too. Let's think about the next number, okay? The next previous number is going to be A, okay? And the next number after that is going to be A plus B. Now let's think about this. Oh, man. Okay, so let's think about this, how we got here. So basically, we're going to have this. We're going to have B, and then we're going to have A, and then we have A plus B. And we do the Fibonacci sequence. And this makes sense, right? So we're saying that this ratio between A and B should be about the same ratio as A plus B over A. These two should equal the same ratio. That's all we're saying here. That's what we're saying here in the Fibonacci sequence. So if you do some math here, which yeah, if you do some math here, so we're saying that A over B equals this thing over here. We're saying A plus B over A equals this thing here. Okay. Then we can do. Then it looks like we might be able to do some cross multiplying maybe. Let's see. A squared equals AB plus B squared. Let's see this. Oh, I understand. cut this out from the main video. Cut this out. Just get the, okay. So we have this ratio here. So notice we can try to simplify this one right here. So we can simplify that to a divided by a. That's 1 plus b over a equals theta. But wait a minute. A over b equals theta. So b over a, that's just its reciprocal. So in other words, the ratio equals 1 plus 1 over a over b, which means that the ratio equals 1 plus 1 over the ratio. From here, we can solve this equation, which I'm going to solve over here. We have the golden ratio equals 1 plus 1 over the ratio. We're going to multiply the ratio on both sides. We get the ratio squared plus the ratio, ratio squared equals the ratio plus 1. You subtract on one side, ratio squared minus the ratio minus 1 equals 0. Here you can get quadratic. You can solve quadratics with the quadratic formula. And then when you're done, you should get the ratio equals 1 plus square root 5 over 2. I think it should be plus or minus. Yeah, plus or minus. And that's how we get the golden ratio. About 1.618. So basically from this, we get that if you take any two Fibonacci numbers, the ratio between them should be about 1.618. That's what the golden ratio is derived from, I'm pretty sure. And then, so that's the mathematical reasoning. And then for whatever reason, this seems to appear in real life. It's very aesthetically pleasing to us, etc., etc. So that's how you derive it, though. Don't look at that. I didn't see that. I wasn't looking at anything. So that's how you derive that. Which I didn't know. I didn't know. I had to look at that to like, yeah. So yeah, that's where the golden ratio comes from. Oh, we're changing the angle. Oh, he's not gonna help? Oh, he's drawing a triangle? All triangles add up to 180. Yep. Oh, right triangle too. Oh, it's a 30, 60, 90 triangle? Oh, special right triangle. They're special because we know all the sides, what the sides are going to be. 45, 45, 90 triangle is also a special right triangle. Oh, we're drawing a rectangle. Remember, all squares are rectangles, but not all squares are rectangles. No way. All squares are rectangles, but not all rectangles are squares. Oh, he reflected it. Oh, he's turning it. And and we got a square. Oh, just gonna it'll become more and more circular as you do this. It'll look more and more like a circle if you just do this forever. Yeah. We got the golden ratio again. The side lengths are some variation of the golden ratio. All the sides are the golden ratio, I think. The golden square. I do think even in studies, I think I could be wrong. I think I read somewhere that like even they did a study where like some of the shapes are just with the golden ratio, like side lengths, and they even chose that one to be the best one. So I think yeah, for whatever reason, we just find it the most aesthetically pleasing. What are you drawing? Oh, it's this Pythagoras. Oh, there we go. We got Pythagoras proving a squared plus b squared equals c squared. Not gonna try to prove that today. I think there are tons of proofs that prove a squared plus b squared equals c squared. I really gonna go about. I gotta go about. Yeah, but a squared plus b squared equals c squared. Very common. It's Pythagoras. How do you even actually? Now I'm curious. Wait, how do we? What's the easiest proof I can go about? Wait, now I'm curious. Time for you guys. Is it just well, you just prove it with the squares? I guess you just prove it with the squares, I guess. Hmm. I actually don't think I know how to prove it. Wait. Hmm. Now I'm really curious. Now I'm now I'm looking at Oh, wait a minute. Wait, I'm looking at Wikipedia right now. Wait, now this looks kind of cool. Wait. Wait. See if I can understand this real quick. This looks kind of cool. Wait. Okay. We have what? A, B, A, B, A, B. Yeah, A, B. What's this proof exactly? Oh, okay. That's okay. I think I understand. So let's say we have this diagram here. Okay, we have this. We have c squared in the middle, since that's what this area is going to be, since it's a square of side length c. And then we have four triangles with side b and a, and right triangles with c on there too. Okay. So our first question is, what is the side length of this full square? This full square is going to be a plus b. That's what each side is going to be. This full area of a square is going to be b plus a squared. That's what this full area should be. This full area should also be c squared, because the area of this square, plus 4 of these small triangles. The area of these 4 small triangles is 1/2 base times height times a times b. Okay. Now we can simplify this to b plus a squared equals c squared plus 2ab. Okay. Now we can simplify this, and we expand this out. We get b squared plus 2ab plus a squared equals c squared plus 2ab. We cancel out the 2, and then we get b squared plus a squared equals c squared. Oh, that's cool. Okay. That's cool. Oh, okay. Oh, that's cool. Yeah, all right. That's one way to prove Pythagoras, I guess. I was looking at Wikipedia. I see like a bunch of proofs. Yeah, okay. That's really cool. Okay, back to the video. Boom. True. It does. We know why. Oh wait, wait. What was with the golden ratio? Were all the side lengths the golden ratio? Oh wait, no. The A and B. Oh, those were the golden. Oh. Does that work? Oh wait, it does. Yeah. Oh wait. Golden ratio to 0 plus golden ratio to 1 equals golden ratio squared. That's really cool. That's really cool. Golden ratio shows a really cool number. Oh, but what's that? Is that fractal? That looks like fractals. You don't know fractals, it's like a really cool image thing. It's the idea is that you have one pattern, and then you zoom in on the pattern, you get the same pattern. Then you zoom in on the pattern again, you get the same pattern, and then you get it over and over and over and over and over again. So those are really cool. What the hell is this monstrosity? I don't even know. Is this like some 12th dimensional being? I don't even know what that is. I know it's making a cool fractal, but I just looks like some Tesseract or something, like from Avengers. I don't know. Oh, true. Oh no. It's just so much faster. Is that another way to express the golden ratio? I'm sure that's another way to express the golden ratio as a infinite, as a specific fraction. It wouldn't surprise me. I'll add it in if it is. But true. Oh, of course, this is also a very famous golden ratio example. It just shows the rectangles, and the swirl represents the size of the boxes represent how the golden ratio expands. So the first one represents like you'll have like I think the area of the boxes increases by the golden ratio, and then if you draw the spiral, you'll get this nice image. Pretty sure you'll see this swirl in like real life. You also see the swirl iconically in the Sonic the Hedgehog design. That's why it looks aesthetically pleasing, no matter what you think about Sonic. So yeah, that's how we get this swirl. It all comes from the golden ratio. I was gonna use it like one of those one wheels. I consider getting a one wheel. Should I get a one wheel? I mean, he's making it look pretty cool there. Oh no. Oh, true. It's golden. Made me a star. A golden star. The golden star. He's making gold and everything. Oh no, he's done. He's done. True. True. He got him in the triangular prism. He got him in the pyramid, the triangular prism. Oh, he's adding. Oh, you got him in the. Oh, you got him in the diamond. He's making a shape. Oh, put him in a cube within a diamond. Oh, I think he's gonna break out of that. Oh, but what if we have a golden shape? Let me make a golden shape though. True. I don't know. Wait, is that 20D? Is that 20-sided die? No, that's not a 20-sided die. That's not a D&D dice. Well, it might be a D&D dice, but I don't know if it's 20-sided. Oh, true. 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 Oh, he's gonna do it. Oh, he put it on the inside. Oh, I got him. He got him. He's done. He can't get out. He's done. And we got nice fractal images. No. But yeah. Well, yeah, if you zoom in on them, they'll have the same pattern. Yeah. You can actually make these nice images in the back too. There are tons of ways to make these types of images. I think I even made one like on About Pi. You just these random walks that look really nice. Oh yeah, actually they don't look like fractal. Actually, yeah, they just look like the random walks. Oh yeah, they just look like random walks. Like you just do like you turn right if we get this number, you turn left, you do this angle if you get that number. That's what it looks like to me. Wonder what number it is. All the higher dimensions. Oh, true? Is that foreshadowing for the physics one? Oh, he fell in. Is this the continuity? How he ends up in the physics dimension? That was cool. Let me start where we began. That's cool. Owl's really cool. Anime versus anime season 2. Wait, no. It's Tech Tuesday. It's Tech Tuesday. It's Tech Tuesday. I can't do real like non-steps on Tech Tuesday. I think I like the music more in the first one, but I'll still thought that was pretty good. Still thought it was pretty good. Dragon curve. That's the curve. Okay, yeah. That's what the curve's called. Like a dragon. Okay. Oh, okay. Okay. I was okay. No, I was incorrect. Fuck. I didn't know the word. Okay. Okay. So dragon curves are okay, they're all fractal light. Okay, you get those cool because they're like self-recursive. All right, I see. So basically the way you build them, those nice dragon curves at the end. Because I'm just on Wikipedia now, because I think this shows it the best, I think. Okay, so you have itself, and then you have it yourself again, then you have itself, and you keep repeating itself over and over again, and keeps making a copy of itself and rotating it. So that's how you make it. Oh, okay, that makes a lot of sense. That's really cool. And then that's how you get those cool curves called the dragon curve. Okay, all right, that's cool. Again, I don't know as much geometry than like just regular math, I guess. In major, I was more of a algebra calc-based guy, not a geometry guy. Yeah, okay. So those were really cool videos. Those were really cool fucking videos, man. Shout out to Alan Becker. I'll watch more of Alan. Yeah. I know my chicken scratch might not have been the best, but hopefully when the YouTube frogs see it, you know, it'll be a little better. I like those videos a lot. Those videos were really fucking cool. I'm gonna watch more of his animations, probably off stream, maybe. But definitely just the whole choreography, everything. Oh my god, the choreography, the music, just the animation, the references, they're all so good. They're so good, man. Oh my god, I love it so much. Thank you, Alan. Thank you, Alan. Keep up the good work. All right. I know this is a short stream, but yeah, I got some stuff to do right now. And do I want to bother playing Celeste? I don't think I do. I just want to. Oh, yes. Oh, love you too. Thank you for joining the stream. I hope you like the stream. You came at a very unfortunate time. Very unfortunate. We just finished the reaction and everything. Oh man, to 2 videos. In fact, that's kind of crazy. That's actually kind of crazy. But yeah, that's a shame. I think I have to go though. Yeah, that's all the stream I got. I'll be back tomorrow around the same time. Oh no, sorry, way earlier. Way earlier actually. So yeah, we got a fun stream planned for tomorrow. Yeah. So hope you guys had a good time. Sorry you guys were late. It is what it is. It is what it is. But yeah. I'll see you guys tomorrow.